Howdy everybody, here's your homework for the evening of 9/11. We're going to be applying the distance formula to what we already know about translations and what we learned today about dilations. Remember that this is called vector notation. It tells you where and how far to go, so direction and amplitude. So our direction, we need to break this down into the coordinate system. Let's look at our x value first. How far do I go in my x value? How far do I go in my y value? And that tells us how we're going to move our shape. So I'm going to take b, go over 3 and down 2, immediately label it b prime. 1, 2, 3, 1, 2, a prime, 1, 2, 3, 1, 2, d prime, and C prime. You'll notice for C, I didn't count it because I saw how my shape was folding in and I could just eyeball it. So here's my prime shape. I performed a rigid translation, 3 units right and 2 units down. Here's what I want to talk about though. I want to talk about the distance between B and B prime, A and A prime, C and C prime, and D prime. Ooh, cool. I made a 3-dimensional object. Interesting. I'm looking at these, my green lines, and they all appear to be the same length, but I want to prove it. I want to prove that these 3 lines are all the same length. So what I'm going to do is I'm going to find the displacement horizontally, 1, 2, 3. That becomes my A value. Then I'm going to find my vertical displacement, 1, 2. That becomes my B value. And I need to find my C value, which I'm going to call D for distance. A squared plus B squared equals my distance. 3 squared is 9. 2 squared is 4. 9 plus 4 is 13. Remember, that's squared. And to get rid of squared, I must square root. So I know the distance of this green line is the square root of 13. Let's just check one more to make sure the distance is the same. I'm going to check from C to C prime. I have a vertical displacement of 2. I have a horizontal displacement of 3. So 2 squared plus 3 squared will equal D squared. 4 plus 9 is D squared. 13 is D squared. Therefore, D is the square root of 13. So yes, the distance is the same when I perform a translation. Let's look at our second example here. It's a triangle this time. And I've written this using directional notation. So this first one was called vector notation. This one is called directional notation. And we put these little kind of arrows on the end that says move this direction. My first value is x, of course, and the second one is y. So we're going to move each point -5, so to the left, 1, 2, 3, 4, 5. And then down 3, 1, 2, 3. So M prime is down there. This is what I see a lot of students do, is they put dots at both locations. Remember, you want to fulfill the whole coordinate change before you put your permanent dot. N, 1, 2, 3, 4, 5, 1, 2, 3, N prime. 1, 2, 3, 4, 5, 1, 2, 3, R prime. There we go. There is our translated shape. I performed a rigid translation of 5 units left and 3 units down. Let's check this whole distance thing again though, because like I'm saying, I want to see if the distance is the same from my original coordinates to my prime coordinates, because it feels very much like it is. But I just want to make sure. If I start at R and I go to R prime, 1, 2, 3, 4, 5, that's 5 units. And then my vertical displacement is 3 units. 5 squared plus 3 squared is my distance squared. 25 plus 9. What's 25 plus 9? It's 34. But I'm not done. There's that one last step to take the square root. So the distance between R and R prime is the square root of 34. Go ahead and find the distance between N and N prime and see if it matches. We had a horizontal displacement again of 5 and a vertical displacement of 3. Do you notice how I'm not using positives and negatives? I'm just saying displacement. How far did I go? I went 5 units. The negative really is just telling me what direction. It's not telling me value. So I went 5 units to the left and I went 3 units down, so 5 and 3. Those are the exact same values from my R prime, so yes, this will also be the square root of 34. So I have a new rule here. The distance between original and prime locations in a translation is constant. So that means the distance between the original and prime locations for every translation is constant. Let's look at one more situation. It's a little different. You've never seen anything like this before. Well, you have, but in 2 parts. Here, I have a translation, but here, I have a dilation. So I can't just count. I actually have to go ahead and make my table. So H, O, and P, get it? Hop. I'm at -1, 2. I'm at -1, -2. And I'm at 1, -2. So I'm going to do x plus 2 and then 2y. -1 plus 2 is not -3. -1 plus 2 is +1. 2 times 2 is 4. So H prime would go at 1, 1, 2, 3, 4. Here's H prime up here. -1 plus 2. So on a number line, if I'm at -1 and I add 2, there's 0 and there's 1. So -1 plus 2 is 1. -2 times 2 is -4. So O is going to be at 1, -4. So here's O prime. And P, 1 plus 2. What's 1 plus 2? It's 3. -2 times 2 is -4. So we're going to go to 3, 1, 2, 3, -4. I had to think about that. When I make my new shape, it's going to look similar, but definitely not the same as my original shape. Ugh, yuck, I'm smearing it all over the place. Gross. Good thing to learn about drawing with highlighters, right? So here's my new shape. When I write my sentence for this one, it's going to have two different parts. I performed a transformation. Not translation, transformation, because I'm changing the size and I'm changing the actual shape. I'm changing the size. I performed a transformation 2 units right and multiplied by a factor of 2 in the y direction. I don't think I'm going to have you do that on the test, but maybe extra credit. So what did we learn? We learned vector notation, directional notation, and this is coordinate notation, but we would also call this transformational notation. We also checked our distance, and we saw that on a translation, the distance stays the same.